Then we are going to have the presentation by Dr. Steve Roffler from Academia Sinica in Taipei, Taiwan, on reversible esterification based liposomal loading.
Thank you very much for this. The talk I'm going to give today is mostly done by this PhD student in my lab. His name is Pierre-Alain Bernhoff. So I give credit to him first. What we're going to talk today about is how to load or retain hydrophobic drug inside the liposome. Sorry, is it this? Oh, sorry. Okay, so we know liposome is a very useful nanoparticle. It's approved by the FDA. It's biodegradable, and you can put different drugs inside of it. But there's still some problems, and so we're trying to solve one of the problems. This just shows the liposomes are already approved by FDA for different applications. So it's one of the more successful nanoparticles. You can load hydrophobic drugs easily. So if you just incubate a liposome with a hydrophobic drug, it will go into the liposome, but mostly in the membrane. The problem with this is it's easy to do, but it's bad because the drug can easily come out. Okay, so it's easy to load, but it's easy to come back out. Most of the drug is just in the membrane. If you have a hydrophilic drug, like doxorubicin, if you can get it into the liposome, it's really great because it will be stable. But the problem is how to get it inside. So we got a fundamental problem. The lipophilic drugs are really easy to get into liposome, but they're easy to get back out. You can't retain them. Hydrophobic drugs are good to stabilize and stay in liposomes, but you can't get them in. Okay, so we try to develop a way to develop a chemical switch that we can control the lipophilicity or the hydrophobicity of the drug in a reversible way. And so the idea is that we add a chemical switch or tag to the drug, and we can make that tag lipophilic to load into the liposome, and then once it gets into the liposome, it can become hydrophilic, so it can be retained. And when it goes into the cell, it can be reversible. That means the original drug can be regenerated. Okay, so the system that we're doing looks like this. We have a original drug. This drug cannot be retained well, so we put a chemical switch on here. It's lipophilic. This can easily go into the liposome, and inside the liposome, it will spontaneously convert it back to a hydrophilic form, so it will be retained. It can't get out. So we can load a lot of this form into the liposome. So this is hydrophilic, and then when this liposome goes into the cell and goes to lysosome, which you heard in the first talk, it all goes to lysosome, is what we want. This tag actually will be hydrolyzed by enzymes in the lysosome to regenerate the original drug. So the tag that we're actually using is a sugar tag. So it's a glucuronide group. Okay, so we have a hydrophobic drug that can't be retained well. We just link this glucuronide. So this is the hard part. You can link this chemically to the drug. And then this is a water-soluble form because it's got a carboxylic acid. We can easily convert this to a lipophilic form for loading. How we do that? We just put this drug into methanol. It's very easy, one step. You put it into methanol, add a little bit of sulfuric acid. You'll convert this into a methyl ester. So you lose the charge. This is more lipophilic, so it can go inside the liposome. Inside the liposome, it's got higher pH. So this actually undergoes another reaction back to the carboxylic acid. And then when this goes to lysosome, there's enzymes will cut this back off to release the original drug. So this is two examples. This is a drug, a 9-aminocamptothecin. It's a topoisomerase 1 inhibitor, anti-cancer drug. And we link the tag through a linker. And so this is the switch tag. This is the water-soluble form. And this is another drug that's also anti-cancer drug. We can also link the glucuronide tag to it. I just want to point out that this drug has an amine group. We can link through an amine group, or we can also link through a hydroxy group. So any drug has a primary amine or a hydroxy, we can do this strategy. And this just shows the original drug, water solubility increases a lot. So for the first case, 9-aminocampothecan, when we put the tag on it, the solubility increases about 600 times, and for the other case, increases about 3,000 times. So this is the water-soluble form. We really increase the water solubility of the drug. And this just shows that we can convert it from the water-soluble form. We indicate with the S as the switch. So these all have the carboxylic acid. This is another case. It's just a commercial. We can buy this from Sigma. It's already got the glucuronide on there. If we just put it into methanol with a little bit of acid, we get the methyl ester form of all these three forms very quickly. And this just shows by HPLC, we're losing the carboxylic acid. It's converted to the methyl ester. So this is the water-soluble form. This is the lipophilic form. So it's very fast and very simple. And this just shows the distribution. That means if we just take a citric acid solution and octanol, and it will form two-phase, and then see where the drugs go, how they partition. The original drugs almost all partition into the octanol. That means these are, this is with the switch. So these all partition into the water phase. That means they're very water-soluble. But when we convert them to the lipophilic form, so we can load these into the liposome, we can see that they have some partition into the octanol phase. So this means maybe they can partition inside the liposome through the lipid membrane. Okay? And this just shows that the lipid form of the drugs, it's stable at pH. So what we do is we make the liposome so the external buffer is pH 5, but inside the liposome is about pH 8. And at pH 5, the lipid tag, the lipid soluble form is stable. Okay, so it doesn't convert to the hydrophilic form. But when we put it at pH 8.2, which will be the pH inside the liposome, this form, the lipophilic form, rapidly, spontaneously converts back to the water-soluble form with the carboxylic acid. So this means it will be trapped inside the liposome because it will become water-soluble. Can't get back out. Okay, so we can load it in, but it can't get out. And this just shows the overall idea. Okay, so we have the drug, we link the sugar to it, and we convert it to the lipophilic form, just in methanol. And then this can go inside the liposome. Once it gets into the liposome, the pH is high. So this will spontaneously convert back to the water-soluble form. And we use calcium hydroxide. So actually this can form complex with calcium, even precipitate. So in this way we can take this originally drug we cannot load well, we can easily load high concentration. If we just take the drug, it's lipophilic. It will go inside the liposome membrane, but it can come out right away. And this just shows we can load very efficiently. So with the tag on here, this is the lipophilic form. It can go inside within 1 hour. And if we just break the liposome and see if it's converted to this form, this is the water-soluble form that can't get out, it's also pretty fast. Within 1 hour, it's being converted to the form that's trapped. Okay. And this just shows if we try to load with the hydrophilic tag, it cannot get into the liposome. Okay. That just shows that by converting this to the lipophilic form, we can get about 200, up to 200 more times drug loaded into the liposome. Okay, this also implies it will be trapped. And we can get pretty high loading. Okay, this one is pretty lousy, but these are pretty good. Okay, and most of the drug inside the liposome is converted to the water-soluble form. And this just shows a couple examples. So this is an original drug. You see, it's a very lipophilic, so we can get it to load into the liposome. But if we put it into a biological buffer, within hours, we've already released maybe 40%. So you get this rapid release of drug from the liposome. This is the problem. But with our tag, we can see that the release is better. We're still getting some, but we've reduced by about 3-fold. And you can see here, we're also getting some crystal forming inside the liposomes. Okay. And in this case, we got much better results. Here, this original drug is released about 60% within a few hours. With our technology, it's basically nothing is coming out. Okay, so it's very stable. So we've taken something we can't load normally stably, now we can load it stably. And this shows the process is totally reversible. So here we start with the parental drug, and we put on the tag. So that's this thing here. Okay, the second peak here in blue. And we can just convert it to the lipophilic form for loading. Okay, that's peak. We change the pH, it comes back to this form. Okay, and then if we add enzyme, lysosomal enzyme, we can regenerate the original drug. So it's a reversible process. So the idea is that we can take the drug, load it in the liposome, and trap it with the hydrophilic form. And then when this particle, liposome, goes into the cell, it will go to lysosome. And liposome will be degraded, and then this tag will be cleaved by an enzyme, beta-glucuronidase, that's present in the lysosome. Okay, and this just shows if we take cells, okay, cancer cells, and we add our liposome, we can measure the free drug really being regenerated into the culture medium. And if we don't add cells, the drug is not coming out. Okay, and if we block uptake with an inhibitor, we also don't see conversion. So these particles, the liposome, have to be uptake by the cells. And if we just do in vitro with cancer cells, we can see that compared to doxosome, it's kind of the gold standard. We're getting similar cytotoxicity in vitro, maybe a little bit better. And we've done a pilot study in a solid tumor. This is a human cancer, breast cancer, and we can see that, okay, it's not well controlled. This is a very pilot study. So we just did control with no treatment. Basically, it's just a tris buffered soline, tumor grows, and when we use our liposome, the tumors shrink. Actually, they all cured. And we see that the weight, we got some weight loss, but it's quite minor. Okay, so this is hassle to make the first synthesis, but once you got the synthesis done, you can trap a lipophilic drug inside of a liposome, and you can generate it in the tumor. And we think it has some advantages compared to other approaches. And I still got 35 seconds, so I'm just going to say, oops, I lost my last slide here. Oh, we have two posters I just want to also mention. So some other work in our lab, we're making bispecific antibodies that can bind to cancer cells on one arm, and the other arm can bind to PEG. So if you got any nanoparticle has polyethylene glycol, we can target it to cancer cell. You just mix it with your particle, and it will target. You don't have to do any covalent attachment. And we have another study where we made an assay to measure anti-PG antibodies in patients, and we found about 40% of people, healthy people, have anti-PG antibodies. Okay, so this is another poster. You can go take a look if you want to see the details. Okay, thank you.
Okay, questions? Right, please.
What is the size limitation for the drugs that they can load actively in this way?
We don't know. We've been using drugs that are around, I mean, they're molecular drugs of 500 or 600. If it's like a protein or something, it may not work, right? Yeah. I think, you think of it like a cell membrane. We're just making the drug lipophilic so it can transport across by diffusion. So we're not doing any kind of active transport or something. Yeah.
Would you please say again the retention mechanism, why the intraliposomal localization of those esters are going to be deesterified? I mean, the saponification you...
Yeah. So when we put on the tag, we first make it in the lipophilic form, so it's a methyl ester.
Yes.
So that can pass the
Yes.
lipid.
Right.
Once it goes inside, we control the pH of about 8. Mm-hmm. At that, we have spontaneous hydrolysis because it's mostly water.
pH.
So you just basically saponification. Yeah.
Okay, so
the first reaction we learn in chemistry, right?
Yeah, yeah. So
it's very simple.
Those drugs, so lipophilic drugs are going to be wrapped within the liposome.
They'll be inside the lumen.
Yeah,
And in both of our
liposome,
cases, we
then-
actually precipitate. They actually
and then,
precipitate.
liposome is going to the target the tumor, and then if it is endocytosed, then
It has to be endocytosis. So actually, we originally, the student did this experiment without my knowledge. I said, you have to use targeted. That means we need to use antibody or something to get inside the cell. But he's very stubborn. But it looks like the penocytosis maybe is a...
Then what about the hydrophilic drugs? Hydrophilic drugs?
You say the drug itself is hydrophilic?
Yes. If it is going to work?
We don't know.
Right.
We didn't try. We've been focusing on a hydrophobic drug.
So
Yeah.
still we have 1 minute. Anybody, any question?
That's a
Then-
good question, though, because 5FU
Yeah,
maybe would be a good
please.
target.
Yeah, thanks for the nice talk. About the derivatization of the drugs that you make, you put some kind of link. So you have not the original drug. This can be a problem, or you have to say?
No. So we use a linker
Yeah.
for some reasons I didn't go into today. You don't have to use a linker, but the linker makes it so that the enzyme in the lysosome can hydrolyze much better. Once that glucuronide, that tag is cut, that linker is designed to spontaneously decompose. So the 100% is the original drug at the end. Yeah, sorry, I didn't make this
Thanks.
Okay, thank you. Thank you again. Then the